Okay, so good day. I am Jenelle and Macaraig from grade 12 Kisumbing, and today we're going to be discussing about basic integration. So I'm just going to maximize this. Okay. So let's start. So first, we're going to be having an introduction. So we have a what do you call this? So it would be easier for us to understand what antiderivative is. So we're going to be reviewing derivative first. So our topic title is illustration of an antiderivative of a function. So this is our pre-test, and Sir Mista asked us to answer this, and it is just about derivatives, and it allows us to review from our past topic. So these are my answers. So now let's answer number 1 first. F of x is equals to x cubed plus 2x squared plus x. So we remember the power rule or the theorem number 2 in derivatives. So we can answer this by transferring the cube into a constant of the x and then subtracting 3 to 1. So we're going to be having 3x squared, and then 2 times 2, it's 4. Then 2 minus 1 is 1. So we have 4x. And then we can remember the derivative rule number 1 that x is the, what do you call this? The exponent of x is 1. So if we subtract that to 1, we're going to have 0. And anything that have exponent of 0 will be equal to 1. So here is our final answer. So it goes the same with the other numbers, but in this one, we remember the rule number, I think it's rule number 3 or 1, where we multiply the number from the exponent to the constant of that variable. So in here, we have 3 times 3, so we have 9x squared. Okay, so let's proceed. Okay, so in the previous discussions, we learned how to find the derivatives of different functions. Now we will introduce the inverse of differentiation, and we shall call this process anti-differentiation. So a function f is an antiderivative of the function f on an interval I if f of x is equals to f of x for every value of x in I. The antiderivative f of a function f is not unique. And for theorem 10, if f is an antiderivative of f on an interval I, then every antiderivative of f on I is given by f of x plus c, where c is an arbitrary constant. And using the theorem above, we can conclude that if f1 and f2 are antiderivatives of f, then f2x is equals to f1x plus c. That is, f1 and f2 differ only by a constant. So here we have terminologies and notations that we need to remember. So anti-differentiation is the process of finding the antiderivative. And the symbol, this symbol, also called the integral sign, denotes the operation of anti-differentiation. The function f is called the integrand. And if f is an antiderivative of f, we write the integral f of x dx is equals to f of x plus c. The symbols integral sign and dx go hand in hand, and dx helps us identify the variable of integration. The expression f of x plus c is called the general antiderivative of f. Meanwhile, each antiderivative of f is called a particular antiderivative of f. So now we will proceed to our main topic, which is antiderivatives of algebraic functions. Okay, so let us recall the following differentiation formulas. These are the basic ones that we used in our first topic in first quarter. And these formulas lead to the following theorem, which are used in obtaining the antiderivatives of functions. We apply them to integrate polynomials, rational functions, and radical functions. So here we have the constant rule, the power rule, the derivative rule of sum and addition. Okay, so here are our main antiderivative rules. So here we have the theorem 1, where we add c to any constant. It's unlike the derivative rule that any constant will be equal to 0, so it will be removed. And then here we have the power rule. In the power rule in our derivative rules, we subtract the exponent to 1. But in here, we add the exponent to 1. Okay, so here is our, if a is a constant and f is a function, then here we will, what we call this? I think we will transfer the constant outside the integral sign. Okay, here we have another sum and addition rule. Oh no, sum and difference rule. So here we have exercises that Sir Mista also asked us to answer. And we will be applying the antiderivative rules here. Okay, so for number 1, the integral x squared dx. So we will use the theorem B in here because we will take the exponent of x and we add it to 1. And then we will also have a denominator. We will use that exponent operation as a denominator. And then we will add c, which is our arbitrary constant. So we will have x cubed over 3 plus c. Okay, so for number 2, we have the integral x cubed plus 2x squared dx. So again, like our theorem C, we will transfer the constant 1 outside, which is 1. And then we will, using the theorem D, we will separate these two because we will add it. So we will have x cubed dx, this is our dx here, plus, and then 2, because 2 is the constant of 2x squared. So we'll have 2 the integral x squared dx. And then using theorem B, we will add 3 to 1, and then we will come up with 4. So it will become x to the 4th power over 4 plus, again, the theorem B, 2x cubed over 3 plus c. Okay, we shall never forget c because it is our arbitrary constant. And then for number 3, okay, let us pause first. Okay, and we're back. I'm sorry for the interruption. So for number 3, we have the integral 3 over 4x to the 4th power plus dx squared plus 1 dx. So again, our constant here is 3 over 4. So we will transfer that outside the integral sign. And then we will use the theorem D to separate the 3 variables in here. So then using the theorem B, which is about the exponent, we will have 3x to the 5th power. So why do we have 5 as an exponent? Because we add 4 to 1. And then since we're going to use 5 as denominator too, and we already have a denominator which is 4, we will multiply that. So we have 3x to the 5th power over 20. Then here we have 3x cubed over 3, again, the theorem B, plus x plus c. Oh, so why do we have x in here? Because unlike in the derivative rule, any constant will become 0, but in here in the antiderivative rules, 1 will become x. So we have 3x to the 5th power over 20 plus x cubed, because we simplified it, plus x plus c. Okay, for number 4, we have the integral x to the negative 2 power dx. And then, again, using the theorem B, negative 2 plus 1, we have negative 1. And then use that as a denominator, then add an arbitrary constant. So the answer is negative 1 over x plus c. So for number 5, we have the integral x to the negative 3rd power plus x to the negative squared power plus x to the negative 1 power dx. And then again, all our constants here is 1, and we use the theorem B to separate the variables. And then we use the theorem B to operate on the exponents. Again, negative 3 plus 1 is negative 2, and then use that as a denominator. So we will have negative 1 over 2x squared minus 1 over x plus ln x. Again, remember, 1 over x is ln x plus c, which is the arbitrary constant. And then number 6, we have the integral x to the negative 100 power dx. Then again, theorem B, negative 100 plus 1 is negative 99. Then use that as a denominator plus arbitrary constant c. And then simplify. So we have negative 1 over 99x to the 99th power plus c. For number 7, we have the integral 3x to the negative squared power plus x plus 2 dx. So again, we will transfer the constant 3 outside, and then we will separate all the variables as indicated in theorem B, and then operate on the exponents using theorem B. So we have 3x to the negative 1 power over negative 1 in here. And then our final answer is negative 3 over x plus x squared plus 2 plus 2x plus c. And then for number 8, this is a pretty easy one. So we have the integral 1000 dx. So we will transfer the constant 1000 outside the integral sign, and then add the arbitrary constant. Therefore, we have 1000x plus c. Then for number 9, we have the integral 3rd root of x dx. So the 3rd root x, if we convert that into exponential form, we will have x to the 1/3 power. So using theorem B, we will operate on that exponent. So 1/3 plus 1 is 4/3. And then simplify. So we have 3x to the 4/3 power over 4. So plus c. Of course, we should not forget arbitrary constant. And then for number 10, we have the integral 3rd root of x squared dx. So again, we will convert 3rd root x squared into exponential form. So we will have x to the 2/3 power dx, and then use theorem B to operate on the exponent. So we have 5/3 as our new exponent. And if we simplify, we will have 3x to the 5/3 power over 5 plus c. And then for number 11, we have the integral fourth root of x to the fourth power dx. So if we convert it to exponential form, we have x over 4, which is just 1 if we simplify it. And then using theorem B, we have x squared because 1 plus 1 is 2. So our final answer is x squared over 2 plus c. Then for number 12, we have the integral fifth root of x to the 10th power dx. So converting it to exponential form, we have 10 over 5 or 2 as our new exponent. And then we will add 1 to that. So our answer is x squared over 3 plus c. Okay, so for number 13, we have integral u squared plus u plus 1 du. And then again, we will transfer the constant 1 outside the integral sign, and then separate the variables using the theorem B. Then use theorem B in operating on the exponents. So we have u to the third power over 3 plus u squared over 2 plus u plus c. Then for number 14, we have the integral 1 over 4 v to the fourth power plus v squared plus v dv. And then using the theorem C, we separate the constant 1/4 outside the integral sign, and then separate the variables using theorem B. And then, so our final answer is v to the fifth power over 20 plus v to the third power over 3 plus v squared over 2 plus c. Okay, so for number 15, this is a little hard. I had a hard time solving this because it's a fraction. So after some researching, here's my answer. So the integral w to the third power plus w squared plus w all over w to the third power dw. So we will like in theorem B, we will separate them, the variables. So we will have w to the third power over w to the third power and use that on the other variables. Then we simplify them. So here we have 1 and then 1 over w plus 1 over w squared. And then using the theorem C, we will separate the constant. And then here our final answer is w plus non-w minus 1 over w plus c, the arbitrary constant, of course. And then for number 16, the integral fourth root of y dy. So again, converting the radical form into exponential form, we have y to the 1/4 power dy. Then using the theorem B, our new exponent is 5 over 4. And if we simplify that, our answer is 4y to the fifth 4 power over 5 plus c. And then for our final number, we have the integral. This is also hard. We have the integral p squared multiplied by the third root of p plus the square root of p minus 1/3 to the negative 1/2 power multiplied to dt. So we will simplify. We will convert them all into into exponential form so we can operate on them easily. Okay, so here we have p to the third power over 3 multiplied to p to the third power over 4/3 and use them on the other variables. And our final answer is p to the third power over 3 multiplied to 3 plus 4/3 over 4 all over 4 plus 2 plus 1/2 all over 3 plus 2 plus 1/2 plus c. Okay, so that is our final answer. Okay, and that is all. And thank you for listening. I hope you understood my explanations, because there this topic is hard because there's so much operations going on. And that is all.